Hello everyone, and thank you for attending our June webinar. The topic today is going to be the ModelHawk platform, history and future. So we'll talk a little bit about the initial motivations for creating a tool suite like ModelHawk, and how those still hold true today. We'll give some updates on hardware, upcoming hardware. We'll talk about some recent updates to the tool. We'll give some demonstrations of the tool at work and talk about some peripheral tools that can be used in conjunction with the ModelHawk tools to do control system development. Again, thank you for attending, and we'll go ahead and get started. So why ModelHawk? ModelHawk is a model-based design tool for control software development. So what is the motivation behind the model-based design paradigm? So systems evolve and iterate. You can see here in this image the idealized process. That's a waterfall where you develop your requirements and you do so perfectly. You then design a system perfectly. You then implement that system without flaws or failure. You verify that it works, which you know that it does because you've done everything right, and then you go into production. When in reality, the actual process is more of a loop. You did not perfectly develop your requirements. Your design will have bugs that need working through. It will have exceptions to the requirements that need modification as you move through your development lifecycle. So the motivation of model-based design is to shorten the time of moving through this evolution, because that's the best way to improve your market cycle time, which will ultimately provide you with advantages in time to market and profitability. So the way model-based design and ModelHawk in particular are doing that is by enabling agile development. It's allowing you to hop from each phase of the process from one to the other so that you can make these changes quickly. So ModelHawk is a tool that will facilitate that loop. To get a little bit more specific about how this works, we'll look at sort of the traditional development process where you have quote-unquote paper handoffs. So in this instance, you have an application engineer like myself who is working on the design of the system, developing models, doing simulations, and designing a control solution for your system. Then he writes up, based on his models and simulation, a specification document of some kind. It may not be paper, it may be electronic, but either way, it's a document used to communicate from one set of personnel with one skill set to a software team, which will then implement that control solution in source code. At larger OEM type places, they'll even do this component by component. So after they've developed that component source code, there's a lot of compiling and linking that has to be done to stitch those things all together into an application file that can then be loaded onto the hardware. So when you're using a model-based design tool like ModelHawk, the application engineer like myself can sit on the left, develop his models, and then use ModelHawk to jump straight to source code, and not just that, but to go straight through source code compiling and linking and create an application file that can then be loaded directly into the ECU. This allows you a direct to your target automated build that for the application engineer will speed up cycling and allow, like we were talking about on the last slide, the evolution of the development process to happen more quickly. So that allows you to have prototyping on production hardware, but ModelHawk and model-based development can also be used for production controllers. So you can repurpose high-volume hardware to be used for lower volume applications because you have a low-cost tool chain that allows you to produce control software for that target. This will give you both cost and time savings. So you can see here we've got the image which depicts your sort of left to right development cycle. So in the concept and design phase, the advantages of the model-based tool are that you can use ModelHawk to do concept verification, design validation, all on your eventual production hardware. And then that way you can do your harnessing and other peripheral parallel efforts for developing your system in parallel, so that way you can quickly move right into production fleet management and service, and the other production tasks that come when you're developing and selling product or systems. So this will avoid the extra iteration cycles that you would need to move if you were using development hardware initially, and then you needed to change to production hardware. This removes those extra iteration cycles that are needed to integrate that hardware with your software that you've developed. So talking a little bit about these production hardware options. So there's a good line of controller hardware from Woodward that can be used in a variety of applications. So here you can see a sort of comparison chart of a few of your options, and we'll have another slide with more. So just to sort of work through these, we've got engine controller modules, general controller modules, and also hydraulic controller modules. That's the ECM, GCM, and HCM that you see. So the smaller modules, the 24 pin, the black ones on the left, we at New Eagle Consulting have used those on a variety of sort of lightweight applications, things like detecting, vehicle presence switches for safety applications, some CAN gateway type of applications. The 48 pins moving to the right can be used on small engine applications a lot of times. They're a good option for those if you have a sort of 4 to 6 cylinder engine, and they can do full authority engine control, controlling spark, fuel, and air. So sort of moving forward to some more options, we've got a 70 pin here on the left that's similarly appropriate for a lot of CAN gateway applications. It's a low-cost module. We've got a newer 70 pin that's coming out that we'll talk a little bit more in depth on in some following slides. The 80 pin module, that's been around for a while doing engine control applications. And then the 112, we've used that in a lot of applications. And in addition to engine control applications, you can use it for similar embedded control system solutions. So that'll include hybrid electric vehicle applications, electric vehicle applications. We've done some turbine applications with this module as well. So a newer sort of similar I/O count module we have is the ECM, the SECM 112 as it's called. It's to the right there with the Freescale MPC 5642 processor. So this has a little bit of a beefed up processor. It's got similar I/O, some of which can handle peak and hold. And it's one of the nice features is it's got 2 microprocessors, so you can use it for safety critical applications. So continuing to talk about this newer 70-pin module, it's one of the new ones that Woodward has come out with. It's, like I said, appropriate for full authority engine control for 4 and 6 cylinder, 4-stroke spark ignited engines. It can be used for gasoline and also alternative fuel engine applications. It's got sequential injection or aspirated gaseous engine control capability. So to talk a little bit about what that has for I/O, we've got 6 injector drivers, 3 of which can handle peak and hold if you need to do sort of an aspirated gaseous fuel control system. We've got 6 electronic spark timing outputs, an H-bridge for throttle control, 9 low drivers for doing peripheral I/O, and some lamps. And then inputs to sort of traditional engine things. You've got VR and digital crank position and cam position sensors, only digital on the cam. Up to 14 analogs and 5 digitals of frequency input, some O2 and NOx sensors as well, and it's got 2 CAN channels for doing integration into your vehicle. So just from the higher level, it can work on both 12 and 24 volt systems. It's got standard automotive operating temperature range and vibration and shock requirements. EMI and RFI specifications, it's qualified for these standards. And again, working on the SECM 112 that we talked about briefly, it's appropriate for on-highway applications. I mentioned earlier the dual micros that make it appropriate for safety critical applications. Like the 0904 112, it can be used for a variety of other applications as well, such as hybrid electric vehicle applications, turbine controls, things of this nature. So you can see from the shape, it's got a little bit more heat-seeking requirements due to its peak and hold power drivers. And again, one of the nice things about this module is its dual microprocessors that can sort of facilitate doing a safety critical application where you need to do sufficient redundancy. So talking about the I/O here, we've got 8 injector drivers, 6 of which can do peak and hold, so 8 ESTs as well as electronic spark timing, electronic spark triggers. You've got 2 H bridges for driving 2 different throttles if you've got EGR or something in your system, 19 low side drivers and attack. On the input side, you've got crank and cam, a variety of analogs and digital inputs, and quite a few speed inputs. Then you've got 4 narrow and 2 wideband O2s. So you can start integrating here after treatment systems using this module. You've got 2 knock sensor inputs and then 3 CAN channels. Similar to the SECM 70, we've got 12 and 24 volt system capability and sort of traditional automotive level mechanical requirements. So moving forward to the software, what are the advantages that the MotoHawk software toolchain adds to this hardware? So you get a consistent application development interface across all of those ECU hardware options, so which helps to make the software very portable. It's quite easy to change your software application from one of these Woodward modules to another. It's almost as simple as just changing the option in your target definition block that'll be in your model. And we'll open up MotoHawk and show that a little bit later. Additionally, you'll need to sort of rescope the I/O mapping, but that's sort of necessary in any case. Additionally, you can leverage some training and infrastructure across the product. So actually right now in the room next to me, we have MotoHawk training going on here at New Eagle in Ann Arbor. And all of these modules that we get can be used for prototype or production. The process is the only difference used between the two, how much rigor you put into your development process. So what are the tool chain updates recently? Like I said, we'll open up the tool and look at it, but to sort of summarize some of the release notes, there's been some improvements on a variety of features for new hardware that Woodward has coming out, including development on FPGA stuff, Ethernet, TCP/IP protocol. The Flex encoders had some feature set improvements, quadrature additions. They've doubled the level of MotoTune security access levels to 8 from 4. Spread out the DLL naming and added some new behaviors such as a digital filter definition and current source, and added some features to the triggers. The other tools that work in conjunction with MotoHawk are MotoTune and MotoService. So MotoTune will be your calibration and engineering interface. MotoService is more of an end-of-line tool used by service technicians once you've entered into the production realm. So you can see here, this is a photograph of what's sitting next to me on the desk right now. So I've got a 48-pin GCM module, which has an H-bridge driver. So I've got a throttle body, power supply, and a SmartCraft hub. So we're going to open up and look at an application, a sort of canonical application that works with developing a throttle body controller. So bear with me for a second while I pull that up. So first, we talked in the beginning about how the first thing that really happens in application development is you have an application engineer who's familiar with the mechanical system and will work on developing controls. And so he'll model things and verify that his control works in that sort of space, leveraging the MATLAB tool set. So you can see we're doing that here. So I have a plant model of my throttle body that you saw in the photograph, and also a controller. So you can see here if I hit play, we're just doing some simulations, giving it a step input. The yellow is the set point that we're sort of stimulating in this simulation model, and then the pink or purple is the response. It's not the best tuned PID controller in the world, but it's showing you that the controller works, and then you can sort of iterate like we talked about quickly, going back to the requirements, back to your design, and testing that it meets requirements if you had, for example, rise time, overshoot type requirements with how you wanted your throttle to respond. So we're sort of run that. We'll hit stop here. But you can see if I go underneath my controller here, I have this control component that's actually linked to a library. And then if I pull that up in my target model, that same software component is being linked to. And then this is a model that will be using MotoHawk to target my hardware. So I can hit Control B and do a build directly to an application file that can be loaded into the hardware I have sitting on the desk next to me. Um, so why don't we go ahead and look under the mask and look at our code real quick. So we've got a state flow with some temperature levels and warnings and a PID controller. Really, I just want to sort of show you the block set a little bit, some of the improvements therein. So you can see, I think, one of the recent developments, go ahead and disable the link there, is this unified interface. You can see as I resize these blocks, they sort of are aware of that and will recalibrate what's being displayed on the mask so that it continues to look nice. If you contrast that with pulling up version 2012, you can see if I resize things down, they get sort of cramped, you know, and don't change. Don't shorten the name or anything like that. So I think that's a nice improvement to MotoHawk in recent releases. It keeps my model looking nice, which I appreciate. And it's sort of unified across all your blocks. So you've got you know, calibration blocks, probe blocks, they're all doing the same thing. Let's look in our, so what else we have here is we have a PWM output to drive our H-bridge. We talked about how portable and portable the MotoHawk toolchain makes the software between pieces of hardware. So you can see I'm just selecting which resource I'm going to use here. And then if I wanted to change my target, I can do so at the top level using this top level block. Going back, we also have CAN messaging for, you know, vehicle integration. If I open this up, this is using a toolbox that New Eagle's added on top of MotoHawk to facilitate CAN development using a DBC file. So you're presented with a graphical user interface that allows you to read from a DBC file and select the messages that you want, and it'll automatically handle all the gains, offsets, byte packings that MotoHawk needs to know about to properly build your application. So those are the outputs. We've got similar things on the input side. So then once you've built that, I won't do the build online here, but it takes, you know, 2 to 5 minutes. You can flash that into a controller. So that controller you saw in the image sitting next to me, I have flashed with that software. So you can see it's reading in set point of 13. It's sensing the position of the throttle sensor at 13. Hasn't triggered any temperature warnings or faults because it's only receiving a 0 temperature currently. But that's the application. So we'll head back to the presentation for a second here. So moving forward, we talked about using MotoHawk as a production development tool. So we've laid out here sort of a design evolution like we talked about earlier, moving on the left-hand side from concept development through to service. So you've got MotoHawk, it's a rapid prototyping controls development tool, and that gets you through your concept, designing the concept and doing validation thereof. Hopefully somewhere in the validation phase you stop messing with your software and you start working on the calibration and other testing. And that's where MotoTune will come in. So MotoTune is the tool we just showed. It gives you an Excel-like interface, presents you with all the display variables, and you can do calibration management therein. And then once you get towards production, you have the Moto Service, which is a similar tool that allows you to do reflash of the controllers or upgrading of the software packages, and then also displaying variables that are accessible by the service level, security level. So that service interface will come in at the end towards service. Then at New Eagle, we've got some tools that we use to work with MotoHawk applications. So RaptorCan and Test, so that's a CAN-based development tool, and then a script-based automated testing tool. So that's sort of what we will work with on MotoHawk projects to do validation, or at least to accelerate validation, and then also telematics for doing, you know, firstly remote engineering data collection, then also fleet management interface. So we'll talk briefly about each of these tools, and then we'll show you them to you as well, and hopefully exercise our MotoHawk application a little bit more. So RaptorCan is just a sort of light-featured CAN development tool that's DBC aware. So in the same way we loaded a DBC file straight into our MotoHawk application, we can use this tool to load a DBC file to do development and test our application with CAN messaging coming in. So it's got a sort of small feature set for monitoring, simulating, logging, analyzing, and replaying logs for CAN data. So a couple updates that we've done recently are some stability improvements and logging feature additions, and then searching the DBC file. And so Raptor Test, this is, like I said, a script-based test tool that allows facilitation of testing your MotoHawk modules. So you can use a couple MotoHawk modules, set them up in the configuration shown in the image in the bottom right hand there. So you can have a module that's under test, and then additionally a coordinator module that's connected to the module under test through some test harness. And then you can use the test scripts to access calibrations, overrides, probes, CAN messaging on your coordinator module to stimulate I/O, and then verify on the module under test that that I/O is stimulating the proper response in software. And so then the tool, you write the scripts, you perform the tests, run the automated testing, and you'll generate some test reports. So that's a compatible tool that we like to use to accelerate verification the same way we're accelerating the development with MotoHawk. You can see a little bit what it looks like here, and again, we'll open up the tool and show you a little bit how that works and feels with the MotoHawk module. Then telematics, it's a telematics tool that allows for remote vehicle monitoring, GPS enabled, so keeping track of location history. You can do some applications on the back end with geofencing and similar things, fault reporting. One of the nicest features of the New Eagle Telematics offering is we can do over-the-air ECU software and calibration updates for supported ECUs. So that means that your MotoHawk module can be in a system across the country from you, and then from your desk you can set up a software package update that can be pushed over the air. And then we've got a protocol that needs to be in place on both the telematics module and your MotoHawk module, basically to ensure that your MotoHawk module is the software is in a safe state where it can be allowed to reflash. And this is all done via a simple web interface at telematics.neweagle.net. This is sort of what that interface looks like. So that's the end of the show. We'll go back to some of the tools to demonstrate what we're talking about. So we've got, again, opening MotoTune back up. We talked about being able to look at the display variables. Here we're plotting the set point versus throttle position. We'll also open up so you can see what it looks like, a calibration where you'll do calibration interfacing. The module I have here on my desk is a flash module. Otherwise, you can do real-time calibration updates right here from MotoTune. So then we'd also talked about RaptorCan. So we'll start playing some CAN messaging on the CAN bus. The application we developed is taking the set point for the throttle over CAN. So now using the RaptorCan, we can start stimulating that. And right now it's set to 13, which is sort of the idle position. But if I scroll this around, you probably can't hear it through my microphone, but the throttle's sort of chasing this knob as I've done it. Oh, and you're seeing MotoTune's now showing that the throttle position set point is chasing, or the throttle position is chasing the set point that I'm sending it over CAN. So this illustrates a little bit how you can use the CAN tool with your MotoHawk module to sort of stimulate the application and test that it's doing what it ought to. So that's the simulate functionality. The monitor, you'll just see we had some messages sending out. The TPS, for example, is back to where we had it based on these commands. And the other thing we can do is we can crank up the temperature, the ambient temperature that the app is receiving. Once you get past 100, you should see we've got a fault. If you go back to your MotoHawk module, go into the controller, you see that once that temperature got over 100, we have a warning that we've set up in our application. So that's another way you can test the application, is by looking at the CAN received as well and making sure it behaves properly in response to the CAN that you're sending. So the other features we won't get into here, but you can log CAN. If you have a full vehicle bus, you want to take a log and analyze offline, you can do that. Analyzing the log, that's if you've got some raw CAN logs that you want to convert using the DBC awareness built into the tool. And then replaying a log is nice. So if you've got a vehicle out there, you can log what's happening and then replay that at your desk to try to stimulate your MotoHawk software and do some debugging. So that's that tool. We'll close these down and then open up Raptor test. So you can see we talked about the script-based test interface. So you can see a script here with sort of step-by-step stimulation of the model that you can do. If we can go over here into run, we can see we can run this full battery of tests that we set up against our controller. Hopefully you see it's passed. Again, I don't know if you heard, but the first test is actually stimulating the throttle body controller that we have hooked up to, or the throttle body that we have hooked up to our controller. The rest of these tests are sort of stimulating the mode state flow that we have built into our application. And you can see that they all passed. If they hadn't, we could go back in here and look at what set of commands and verifications we're doing with the MotoHawk software, go back into our model and start the debugging process. So to go back, early in our PowerPoint, we talked about this automated executable to model to executable build engine, and you've got the application engineer sitting all by himself on the left here. So hopefully the use of the tools that we went through illustrates sort of how you can jump through each part of the evolution cycle and sort of do your application work without having to do the churn during each evolution of handwriting paper specifications and handing them off to a software team for iteration. So to talk more about what's up and coming, we referenced briefly some more hardware coming from Woodward, so we look forward to that in the future. We saw a couple of their newer hardware offerings and these types of applications that they'll be applicable for. We went through some updates in the software tool chain with MotoHawk, showed some of those, and then we showed sort of how you can use MotoHawk and some peripheral tools with it to quickly develop, debug, validate applications as an application engineer without having to do a lot of churn in the software space. So at this point, I think we'll start opening things up for any questions that we have from the panel, if we have any. But if you have any questions, feel free to post them on the webinar here, and we'll get to them. Like I said, the other support that comes with the MotoHawk toolchain is we at New Eagle will provide an infrastructure including support, training as is happening right now, and support, engineering support as needed. Thank you very much for your time and for coming. Like I said, we'll hang tight here for a couple questions if they come in. All right, it looks like we're light on questions, so maybe we'll end here. But again, thank you very much for coming, for taking time out of your day to hear some about the MotoHawk platform's history and future, and hopefully we've proven that the initial motivations for creating the model-based toolchain are still valid today, and how we've sort of improved upon them in the context of your development effort between concept verification all the way through to production. Thanks very much.